Hello, good afternoon, everybody. Thanks for joining us for this webinar titled Control Schemes for Dealing with Nonlinear Mechanics. This webinar is brought to you today by Design World and presented and sponsored by Galil Motion Control. So before we get going, I'll mention a few housekeeping points of order. At the bottom of your screen, you'll see a number of widget boxes. These can be moved and resized to your unique preferences. You can open, close, and change the layout as you like. Also, at any time during the webinar, you can ask a question, and after the presentation, we'll have time for some Q&A. We'll get to as many questions as we can. You can also tweet about the webinar or any interesting points you may hear here. Simply sign in through the Twitter box. So my name is Miles Budimir. I'm a senior editor covering motion control with Design World, and I'll be moderating the webinar today. So let me tell you a little bit about our presenter today. That will be Robin Riley, who is a senior applications engineer with Galil Motion Control. He joined Galil in 1999 as a applications engineer. Before coming to Galil, he worked at companies such as Raychem, Tyco, and EPE Industries, where his technical contribution focused on mechanical design. Robin began his career at Galil, helping customers with the design of new hardware, software, and firmware for their motion control applications, as well as troubleshooting existing OEM applications. So in the past 16 years, Robin has become the senior applications engineer, focusing mostly on international OEMs. And Robin holds a BSME degree from the University of Maine at Orano. I hope I said that right. Probably didn't. So without further ado here, I'll hand it over to you, Robin.
Okay, thank you very much, Miles. Again, yes, my name is Robin Riley. I'm here at Galil Motion Control, and the title of this webinar is Improving the Performance of Nonlinear Mechanics. This webinar is really tailored for engineers who have a mechanical system in front of them, and for whatever reason, it's simply not meeting the performance expectations that were developed at the outset of the application. Something about the mechanics is funky, meaning the response of the controller or the controls can vary over time, over distance, on a day-to-day basis as the end customer changes the payload. Just some reason why the mechanics aren't operating as ideally as they absolutely can. And the questions are really what can be done about them with a minimum of additional cost and or effort. So real briefly, the agenda. The very first thing I'm going to do is introduce who Galil Motion Control is and what we can potentially offer. And then I'm going to jump right into the meat of the webinar. The first application is going to be talking about a high friction axis, where it simply takes a lot of effort for the motor to initiate the motion, and what can potentially be done to limit the errors that would occur overcoming that additional friction. The second topic to discuss is going to be mechanics that have excess backlash, which is a very common thing for most electromechanical systems to have to deal with. And there are definitely some tips and tricks that we'll be able to incorporate. Next up is going to be talking about a servo mechanism that incorporates a spring, which is never an ideal solution, but sometimes that's the only way to move forward. Next up, we'll be discussing an axis that is exposed to large and unpredictable outside forces. So no matter how carefully the engineer designs the application, there's expected to be all sorts of disturbances that aren't necessarily going to follow a specific set of rules. Next up, we'll be talking about mechanics where the inertia varies with position. Again, very common in the field of robotics and things like that. The last application to discuss is going to be a hydraulic axis and what using hydraulic fluid to force motion, how that is potentially dealt with within a motion controller. I will then summarize the discussion, and then we'll move straight into the Q&A. So first up, just a real brief introduction to Galil Motion Control, if you're not familiar. We have been in business since 1983. We were founded by Dr. Tal and Wayne Barron, who are still involved in the company to this very day. We were the first company to introduce a microprocessor-based servo controller. It started out as an 8-bit single-axis servo mechanism for a very specific application, But after that became successful, the founders were able to evolve into a great deal of number of industries, as well as a high access count, high I/O count, and much higher performance than we had back in the 80s. We have delivered over 750,000 motion controllers and PLCs, the vast majority of which are still in operation today. And then lastly, I just wanted to mention that Galil really prides itself on the technical support and service of the product. About 1/3 of the company is devoted to technical support, of which I am a member of that team. In addition to what the factory has to offer, we do have a worldwide network of factory-trained reps and distributors that can help with our engineering friends in any time zone throughout the world. The technical support team that I mentioned, we do have over 100 man-years of expertise. We have mechanical engineers, electrical, computer science majors, a wide variety of expertise to be able to help out with your application. And then finally, there's a great deal of information available on our website at www.galil.com. I encourage anyone who's listening to go out and check it out. Okay, so this is the first axis to discuss. This is where an application has what would be considered excessive friction, static friction in particular. For this application, I'm using what would be called a microarrayer, where there is a series of glass pipettes that need to be positioned very carefully over a series of pockets on a sample tray. And once those pipettes are properly located, then a small, precise amount of fluid is dispensed into those pockets. And as you can imagine, those glass pipettes are not only very delicate, but they also they're very prone to being shaken out of position. So a great deal of care has to be taken in causing nothing but smooth and graceful motion. Otherwise, you're going to have to deal with problems with those glass pipettes. So here I show a 3D view of the application. For convenience sake, I have removed the bellows from covering over the lead screw. The bottom left-hand corner, you can see I have a relatively small motor that was selected not only because of budgetary constraints, but because of physical space constraints. And because of the relatively high load of the glass pipettes in the carriage, it takes about 50% of the available motor torque to even break static friction. So you can imagine if the motor was commanded to move very aggressively, it's going to end up causing a great deal of shock to be felt by those delicate pipettes. So the questions really are, how can we minimize that without a great deal of additional effort or changes in the mechanics? So here are some of the tools we have to address these high friction axis types. The first thing to look at carefully is profile generation in order to minimize jerk. Now, what a profile is simply the way the engineer describes to the controller the overall shape and characteristics of the motion. So the speed of the move, the acceleration, the deceleration, and of course the distance. So as you develop the application, the goal would be to choose those parameters in such a way that you're not causing heavy amounts of jerk, aka the rate of change of acceleration, which can cause additional shock to be felt by those mechanics. So by careful profile generation, we're going to be able to control the jerk as best as possible. Next up is a velocity feed forward component, which is what is known as an open loop filter. And I'll get into greater detail about the difference between open and closed loop filters here in a minute. But the velocity feed forward parameter is capable of generating motor torque the instant that motion is commanded. So you're not having to wait for position error to build and the PID filter or the closed loop filters to rise in their output and eventually break friction and cause an overshoot as things start to move. So by initiating the move via the open loop velocity feed forward, we're again able to minimize the shock felt by the mechanics. And then the last tool in our built-in toolkit is going to be attempting to overcome the friction in both directions by using bidirectional anti-friction offsets. Ideally, the force of breaking friction is the same in both directions, but that is by no means guaranteed. So it's nice to have the tools available to set not only a forward friction offset, but also a reverse friction offset. So here's what we came up with as first solution. First thing we did was we generated what's known as S-curve velocity profile. So instead of having just an instantaneous transition from being at rest to accelerating, We are instead going to ramp the acceleration over a certain period of time. And the way we do that is by using what's known as PVT mode of motion. PVT is short for position, velocity, time. So for every segment of motion, you command a distance to travel, a time to travel that distance in, and a velocity at the end of that segment. So position, velocity, time. That's a very good way to constrain the overall profile with any arbitrary velocity and accelerations. So what I'm showing here in this chart is a plot of a S-curve motion. So the red line here up on top is the filtered velocity of the a-axis. And just real briefly to introduce you to the Galil lexicon, Galil's programming language uses two-letter English-like mnemonic commands. So for example, TV is short for tell velocity. TVA is the a-axis velocity. So the first line, that red line, I'm plotting the velocity of the a-axis. And then the lower line you can see is RP, which is short for the commanded position of the a-axis. And you can see that that's a nice, smooth, S-shaped profile. So in addition to commanding PVT motion with true S-curve, we went ahead and used our velocity feed forward, or FV parameter. And that, again, generates torque at the moment that motion is commanded, as opposed to waiting for the PID filters to spool up and generate torque by themselves. And then lastly, as I mentioned, we have these bidirectional anti-friction biases, ZP, as in the anti-friction for the positive direction, and ZN for the negative direction. So all those three things were incorporated into the motion, and those really minimized the shock effect that was felt by the pipettes and minimized the overall potential for damage. So here's my second application. This is a system where the mechanics include a certain component of backlash. And again, backlash is something that's very, very common if ever you are using a system where you start with rotary motion and you have to translate that into linear motion, whether that's through a gearbox and then a lead screw, as I'm showing here, or from a motor through a timing belt or a chain, or really any means of transferring motion from a rotational aspect into something linear. So here I'm showing just a simple cross-section of a lead screw. The darker gray color is the cross-section of the nut, whereas the lead screw you can see there in the center. And you'll see on one side of the screws that there appears to be a small black gap. And that small gap, if you think about it, if the lead screw starts to turn in the clockwise direction, it has to travel a certain number of degrees before the leading edge of the screw actually comes in contact with the leading edge of the nut. And then subsequently, if I were to change direction, I'd have to move in a certain number of degrees in the opposite direction before the new following edge of the lead screw comes in contact with the nut. And so that angular translation before motion on the nut occurs, and of course the nut is connected to the payload, that angular motion is considered the backlash. So every time you change direction, you have to add that component of backlash motion in order to move the nut and subsequently the payload to the expected location. Now there are two ways to determine the magnitude of the backlash. The first way to do it is to rely on the data sheets of the lead screw and the gearbox, et cetera, et cetera, et cetera, and sum up what the calculated backlash is going to be. Now that's all well and good, but of course, not only is that the theoretical ideal as far as the backlash is concerned, it's a steady value. So whether it's tuned at the near end or in the middle of travel or at the far end, the calculated backlash is something that is just got a single value. And also, if you calculate it beforehand, you're taking into account the fact, or you're not taking into account the fact, that over time the mechanics can potentially loosen up. And if that's the case, then whatever you calculate based on the data sheets may not be true after 10, 100, or 1,000 hours of operation. So the more appropriate means of determining the backlash, in our opinion, is going to be doing it empirically, where you command the motor to initiate motion, and you very carefully monitor the position of the nut, and after X number of angular degrees or motor encoder counts, you start to see the nut to move. As soon as the nut starts to move, then you stop the motor and you reverse direction. And then you again, calculate how many encoder counts the motor has to turn before the screw begins to move. And that number of degrees or encoder counts is the backlash of the mechanism at that given time. Now for this example, I went ahead and made it very simple, and I just stated that the backlash of this lead screw is 50 encoder counts. And we'll take that into account in one of a couple of different ways. So the tools we have to deal with axes with backlash. Right off the bat, you really come to a pretty dramatic fork in the road. The first is, if you wish, you can implement a very low-cost open-loop solution called Galil's backlash compensation firmware. What we do with this special firmware is every time the operator commands a change in direction, we simply add a backlash component that was predetermined before the move was begun and instantaneously add that to the profiler. So you as the operator don't have to worry about adding or subtracting those backlash counts every time you change direction. The controller does it for you. Now the benefit there is it's very simple, very straightforward. It's a single parameter that you enter on an axis by axis basis. But the problem there is, again, just like as you were choosing the theoretical ideal backlash from the data sheet versus empirical data, is the backlash compensation firmware expects that backlash component is steady across the range of travel and will not grow in time. So if you have an application where maybe you're cutting foam with a water jet and you needed to improve your accuracy from 0.1 inches to 0.01 inches, then by simply adding that backlash compensation, you may be able to meet that performance standard. But for more dynamic applications where you expect the mechanics to wear over time, or because the lead screw isn't perfect pitch, backlash will actually vary over the length of travel, there's a more ideal solution. And that is to look at using what's called dual loop feedback within the Galil motion controller. Now, at the outset, I did mention that this webinar was attempting to present solutions that were exclusively programming tips and tricks. But really, in this case, by adding a relatively affordable additional component, you're able to increase the accuracy of the endpoint or the payload by potentially orders of magnitude. So it really is worth considering if you really need to get to a higher level of overall accuracy. So with the dual loop feedback, what we can do is add a linear scale, also known as a linear encoder, to the payload. So at that point, the motion controller knows the precise location of the payload in addition to the precise location of the motor. And so you may have a question, well, what does the controller do with that additional piece of information? How does that make the overall accuracy better? And the answer really comes down to the way we implement those changes to the overall control law. So for this application, this is the solution we came up with. We knew that over time the backlash was going to grow. Basically, the mechanics were going to settle in and sort of loosen up over time. So we couldn't go with just the open loop backlash compensation. We had to select the additional linear scale and go to the dual loop mode of motion. Now, one comment I have on this additional feedback is the ratio of resolution between the motor and the load encoder. Excuse me. Ideally, the ratio is such that the rotary encoder is at least twice as fine as the linear scale. And the reason why you want the rotary encoder to be more precise is that's where we're getting our velocity information. That's where our viscous damping term, KD, is going to be coming from. And so on a sample-by-sample basis, you want as precise a velocity calculation as you can get. So if the data, for example, was coarser than the linear scale, then you're going to get a very crude velocity calculation, and that's going to lead to a fairly dramatic sample-by-sample variance in the forces generated by that KD, viscous damping term. So 2 to 1 is a good starting point. 5 to 1 potential is even better. Even up to 10 to 1 is okay, as long as it doesn't exceed the overall kinematics capabilities of the control. And then finally, to implement this solution, it's a very simple command. In the Galil universe, it's DV, as in dual velocity or dual loop. You simply enable that mode of motion, and the controller takes care of everything else for you. And so this is what's going to be going on within the controller when you implement the dual loop. So the first thing I have here is I'm just showing the existence of the motor. And by commanding the motor to accelerate, that means I have to first push through that backlash. That then causes the payload to begin to move. And that means that the load sensor is going to present to the motion controller a change in position. So that load sensor data is fed up here. You can see in the top left corner to this first summing junction. And it is compared to this term R. And R in the Galil universe is the commanded position on a sample-by-sample basis. So you take the commanded position R, you subtract the load sensor position, and that difference, that delta, is considered the error. So that is the position error at that given sample. The controller then runs that position error through this block called the PI filter. So the proportional gain and the integral gain come from the error sensed on that payload. And that's what the controller is attempting to minimize, is error on the load, of course. Now, in addition to the motor turning and accelerating the load, it is, of course, changing the position of the motor encoder. And as I mentioned, the motor encoder is derived in order to generate the overall velocity of the axis at any given moment. So that velocity data is fed through our D filter, our derivative gain. Now that derivative gain is then summed with the gains from the PI filter. That signal, which is a 16-bit number, is most likely turned into a voltage. That voltage is sent to the amplifier, and the amplifier, of course, generates current. The current causes that motor to accelerate. So by doing this, you can see the inner loop where the D term comes from this tightly coupled mechanical system where the feedback is mounted directly to the motor, as well as the outer load that has to manage the backlash of the overall system. And by doing this, we effectively eliminate the effect of the backlash on the accuracy of the payload. Over time, if that backlash changes, if it grows, or if it varies from position to position within the application, that's really no problem for the filter. This control law is capable of managing those changes in backlash, unlike the open loop backlash compensation firmware, which expects the backlash to stay steady all the time. So you might say to yourself, well, this is great, this is definitely improvement, but is this as far as we're able to go? And the short answer is no, not really. There are additional ways of improving this even further. And depending on the resolution of the encoder, of the linear scale, the magnitude of the backlash, and a couple other of the mechanical characteristics of the application, you might be a candidate for what is known as the advanced dual loop. Now, the advanced dual loop actually doesn't have a lot of differences to the standard dual loop, but there is one very important difference. So again, here we have the motor, and by moving the motor, we cause the backlash to be taken up, driving the feedback sensor from the load. That load sensor then generates the position error compared to the commanded position as before. But now you can see in the block diagram, I am only using the integrator, the I filter, on this endpoint position data. In addition to that, again, you see with the motor turning, the motor encoder begins to change position as well. And that data is now fed through both the proportional and the derivative gain. So you can see I moved this P term from the outer loop down into the inner loop. So your question might be, well, how does that improve the response and or accuracy of the application? And the short answer is, because the motor and the motor encoder are rigidly coupled, there is no phase shift or delay in seeing that encoder data change position when the motor begins to accelerate. And so by doing that, you can have a very aggressive P and D filters because you're not having to account for that additional phase lag of that overall control scheme. So by doing that, you're actually making the system more responsive, more capable of modifying the motor torque in order to minimize the position error of not only the motor encoder, but also what really matters, which is the load. So here's a real-world example showing some of the final data from a variety of solutions, all using the same mechanics. The first column I show is the single-loop application, where in this case there was only an encoder on the load. The motor was left sort of without knowledge of where that motor ends up being. And so you can see from here that the P, the D, and the I gains, they're very small. Those are actually on the 1 or 2% of maximum value. So they're really, really quite gentle. And the reason they had to be gentle was if they were made any more aggressive, the motor would really start to hunt and become nervous, and you could hear an audible component as it was always attempting to find the target position of the payload. Below this, I show the motion time, the time to move and settle. Because this thing was always hunting around and really never coming to rest, it was considered to not really ever settle. It always was sort of in motion. There was never a point where there was exactly 0 counts of change of position. And then overall, just a point-to-point motion back and forth with a minimum of error, we found that we could get approximately 2 hertz, so 2 moves per second, and that was about all that we could manage with that existing system. But by the simple addition of a second encoder and engaging the dual loop mode, you can see quite a dramatic improvement. So not only have the PID filters grown to something more responsible, where especially the D gain is high enough that it's actually going to be generating enough viscous damping force to keep things stable, but also the motion time went from never to approximately half a second. So we were able to move and settle within plus or minus 1 count of error in half a second versus before we were just always hunting around. And then finally, the bandwidth went from a paltry 2 hertz up to 70 hertz, which is actually a pretty good number for almost any electromechanical system. You're really going to have to start talking about some exotic mechanics in order to be able to respond to an injected move frequency higher than 70 or 80 or 100 hertz. But then finally, I went ahead and implemented the advanced dual loop, which is mostly just a modification of firmware. And you can see, again, by moving that P filter into the inner loop, I see another dramatic step up in the PID filters. So an even more aggressive response from the P filter, better response from the viscous damping from KD, and then the KI term being higher means eliminating the endpoint error was something that was able to occur much, much faster. So the motion time, again, shriveled from half a second to about 140 milliseconds, an improvement of roughly a factor of 4. And then the bandwidth, again, increased by a factor of 4 to something on the order of 280 hertz, which is actually much, much faster than almost any electromechanical system is going to be able to respond. So in summary, as far as mechanics with backlash, the dual loop function is something that's built into the controller. You just need the additional hardware. But if you consider yourself a candidate for the advanced dual loop, or you just wanted to see if that was truly the case, I definitely recommend to contact Khalil, and we'll be happy to discuss. Okay, so the next axis to discuss is a mechanism that is incorporating a spring. In this example, what I have is it's a vertical axis where there is a small platform where a relatively heavy camera is mounted. And the goal is to move the camera up and down in a fairly precise manner. I do that by using a timing belt connected to a rotary motor shown in the bottom right-hand corner. Now, because the camera is relatively heavy, I wanted to have some amount of counterbalance to help the motor stay small and not consume a lot of power, but still be able to precisely position that camera over the range of travel. Now, you can kind of see just from this layout that if no power was applied, that spring is going to extend to a certain position and sort of float in space. That's going to be the ideal length of that spring. But if the spring were to compress or the spring were to expand, at any point other than that natural float point, the motor has to work a little bit harder to overcome the effect of that spring. So here I show a 3 view, and again on the bottom right you can see the existence of the rotary motor. It is connected to that platform via a timing belt. Then the camera and the spring are mounted to that platform. A more ideal way, if there had been space and room in the budget, would have been to use a gravitational counterbalance. That would have eliminated the effect of the spring causing a variation in the motor force over the range of travel, but there simply was not the physical space to add that additional component. So here are a couple of the tools we have available to help incorporate the spring and make it minimize its overall effect on the accuracy of the motor. The first is we need to determine the amount of torque that the motor has to generate to hold the camera in position across the range of travel. Not only at that float location, but maybe every 10 centimeters I move the axis up, and then I determine what the torque is necessary to hold that position, move another 20 centimeters, make a note of that, move another 20 centimeters, or whatnot over the entire range of travel. Now, ideally, that relationship is linear. So for every additional 10% of offset, you should see an increase of approximately 10% of the overall force. I say it should be linear because ideally you select a linear scale. There are springs out there that are called progressive springs, where depending on how much the spring is compressed, the rate of spring constant will vary. And those are mostly used in automotive suspensions and things like that to deal with not only small vibrations but also big hits. But in the case of motion control, that really adds no value. So if you have to incorporate a spring, we strongly recommend you go with a linear spring. So what was the solution? Well, after we determined how much force was necessary to overcome the effect of the spring at any given location, what we can do is write in the Galil controller's memory a thread that is constantly monitoring the encoder position, and based on where it is at any given moment, it can look up that scale factor that we determined before the mechanics were released to the wild, and we know how much force we have to apply in order to overcome that that spring constant. So the first thing we do is we go out and read the encoder value. We then calculate how much offset using the OF command we need to add or subtract to the overall control law to minimize the effect of the spring on the PID or the closed loop response. So we go ahead and set that OF based on the encoder value, and we then put ourselves in a loop. So every 10, 100, 1,000 milliseconds, whatnot, we are able to constantly update that offset command in order to account for that effect of the spring. Now, it's not perfect, it's not ideal, but by doing this, we are at least equalizing the effect of the PID based on rising or falling, or if it's in the middle of travel, or at the far end of travel, or at the near end of travel. So it's not ideal, but the goal here, again, is to overcome some limitation in the mechanics that are helping or are harming you in your achievement of the overall performance spec. So this is just a way to hopefully get you over that final hurdle. Okay, this is a slightly more complicated application that we came up with, where we're basically doing a hull testing. So we're looking at minimizing the amount of force necessary to pull a particular hull design through a wave tank. The overall application was intended to assist engineers in optimizing the hull shape based on a given mass and physical dimension of the watercraft itself. So what happens here is, now it's shortened for brevity, the actual vertical component of this, it was about a 50-meter long wave tank. What you see at the bottom, going to have a small winch attached to a stainless steel cable. That cable go ahead and is attached to the front of the watercraft. On that watercraft, there are two parallel guides to the left and the right, and what those guides do is it eliminates any side-to-side motion. What we're really interested in here is the fore and aft motion of the watercraft. So how much force does it take to overcome whatever wave we're crashing through at any given moment? Now, one important piece of information that's available to us is there is a host computer connected to a variety of sensors mounted across the overall surface of the hull. And those force sensors are able to determine in real time not only the magnitude of the wave force on the hull, but also the direction it's coming from. So this host computer determines that information, and then on a very high rate of data transfer, sends that information back over to the Galil controller. So in near real time, we know not only the magnitude, but also the angle at which these waves are striking the hull. So here's a side view showing hopefully a little bit more information about the way things are organized. Again, the goal here is to pull the watercraft through the wave tank with as steady a velocity as possible, regardless of the shape of the waves, whether it's still water, whether the hull is particularly heavy, or it's a particularly poor design in the hydrodynamic design of the hull. In any event, the primary purpose of the application is to pull the watercraft through with a steady velocity. And we do that by monitoring the cable and making sure that it doesn't go slack or that there's dramatic changes in the tension on the overall cable. So one component of the application was the fact that on a day-to-day basis, the engineers might be changing the mass and or the shape of the hull without without the motion controller having any prior knowledge of that information. So the controller may wake up tomorrow morning and all of a sudden have to deal with a payload that was twice as heavy as it was originally intended for. Now, all that mass information can be transmitted from a host and accounted for in scaling the appropriate PID filters whenever that hull mass changes. So here are a couple of the tools we had available to us. Again, as I mentioned, the host computer has these sensors that are giving us magnitude and angular information about the wave forces. In addition, the controller has the ability to monitor the cable tension on the winch. Now, you might say to yourself, well, as the winch winds up, the relationship between the actual tension on the wire and the torque effect felt by the motor, that might vary. But really, in this application, the drum on the winch was wide enough and there were few enough overlays of the cable that the fact that the diameter of the winching effect changes over time wasn't something that was important to the overall calculations. So that simply was eliminated from the overall application. So here was the solution we came up with. First, because we were getting this constant real-time update from the host with force and angle information about the waves crashing into the hull, we were able to deduce fairly quickly by taking the sine of the angle and knowing the magnitude of the force, we were able to determine how much force was being applied in the direction of travel. So by knowing that information, we were able to add or subtract those forces to the overall motion profile. So not only are we jogging along at a steady speed with a given PID filter, but just like we did with that spring, we were able to add or subtract and offset using that OF command. Now, to eliminate the possibility of cable slack, I've gone ahead and disabled the integrator term, the KI, for this motion. Now, you can say to yourself, why is that allowed? And the answer is really, in this application, what was most important was velocity, steady velocity. We don't really care about steady state error. So as we're moving through the water, if we have a lag of a few counts or even a few dozens of counts, that's not affecting the overall performance. What matters most is that the velocity through the water is held steady. So by eliminating KI, we're not dramatically changing how the filters are responding to error, and that allows a little bit of steady state error, but a much smoother motion profile and hopefully a steadier tension on that winch cable. Now, lastly, because the weight or the mass of the hull might change from test to test, again, the host computer can transfer that information to the controller, and the controller can then scale its filters, specifically the KP term, based on the increase or decrease in the overall hull mass. Now here I just wanted to touch back again on a difference between open loop and closed loop gains. As I mentioned, we have several filters like that OF term, the FV term, the anti-friction biases. All those things should be considered open loop gains. Now in this application, as you know, we're basically towing a watercraft through water. And you can think to yourself, well, no matter what, even when the water is still as glass, it still takes a certain amount of force to pull that hull through the water. So instead of relying on excess position error and the PID filter generating torque based on that position error, why not generate that force from the outset? So don't wait around for the error to spool up, but say, as soon as I go, issue a command that includes that open loop force. And that's what these terms FV and OF do. Is as soon as I say begin the motion, it says, well, I'm commanded to move at 1 meter per second. Therefore, I need to generate 1 Newton meter of force, or whatever the relationship is, in order to pull that boat through still water. Then, riding on top of that, we'll call it a DC force output, are the closed loop gains, the PID filter. In this case, the KP being the most important. So instead of having all the torque generated by these closed loop filters, instead maybe 70% of the force is generated open loop, and then this closed loop signal should ride like an AC signal on top of that steady DC output from the FV and the OF. So by combining those two, the open and the closed loop, you're really able to take advantage of the way to move things through whatever time and space are necessary without relying exclusively on position error being the driving factor. Okay, the next application to discuss is, again, very common in the fields of robotics or somewhere where you have non-Cartesian motors and mechanics needing to perform Cartesian motion. So in this example, I have an anthropomorphic robot arm. It's got 3 axes. It's got a shoulder, an elbow, and a wrist. And what we're doing is we're involved in the 3D welding application. So, we're welding the sheet metal to automotive doors. So there's a need to follow a very complex path through three space, but the calculation of the motor positions have nothing to do with the Cartesian locations of the end effector. Now, what you can see sort of from this side view is that when the arm is fully extended, the load, which is on the left, asserts a fairly high amount of force on the shoulder and the elbow joints. But as I would retract the arm, you can kind of theorize that the overall forces being felt by those joints will be minimized, especially when the motor ends up being completely vertical. So again, in a welding application, you're going to have a relatively large payload. In this case, I'm just indicating it by those 3 blocks. And in this application, because on a day-to-day basis they may be welding thicker material or they may be using different welding techniques, that payload might change from today versus tomorrow. So the overall control scheme has to take into account the fact that that payload might change. Again, the bottom right corner shows the shoulder joint, which is going to feel the effect of all things above it. And everything I say about the shoulder joint also applies to these others. But for simplicity's sake, I'm just keeping things limited to that first joint. And then again, because this is welding, the overall important thing is not only accurate positioning, but also very steady velocity through Cartesian space. If it was to go too slow, we would end up blowing through the metal. And if we were to be moving too quickly, we would get incomplete welds, and therefore we would effectively be ruining the workpiece. So what are the tools we have to deal with this fact of varying inertia as position changes? Well, the first thing to know is on the Galil controllers, you as the operator are capable of changing the PID filters on the fly. So it's not like you have to go to a special home location or disable the drive to change the PID filters. You can change them as the machine is in operation. Second thing to look at is the fact that a host computer is capable of telling the controller that it has a new payload to have to worry about. So if, for example, tomorrow the payload is half as heavy as it was today, that information can be relayed to the controller, and the controller can then self-scale its PID filters to, again, avoid any sorts of overly aggressive or overly gentle response to error. Now, one final thing we can do to help us minimize the error over the range of travel is we can tune the axes in various locations. So we go ahead and we tune the axis when it's fully extended, when it's fully retracted, and maybe 5 or 10 locations throughout. And that information can then be written into predefined arrays in the controller's memory. So there would be one array for each filter for each axis. So in this case of 3 axes with 3 filters, we would end up having 9 total array elements. Now I do suggest that it gets tuned with the heaviest expected payload. Then if that payload were to decrease during operation, you can always just scale back the PID filters. That's as opposed to tuning with the lowest possible payload. At that point, you never know how the controller is going to respond if for some reason the operator uses a very, very heavy payload. So I recommend starting at worst case and moving backwards. So here was the solution that we came up with. Again, we used the PID filter values that we determined as we tuned throughout the ranges of motion. And then we dedicated the thread to, just like we did with the spring, monitoring the encoder positions, looking up in the array table where we currently reside, and interpolating between subsequent values to set the most appropriate PID gains for that position. That loop, that kind of control scheme is called gain scheduling. And that really is a nice way to have the controller dynamically adjust its PID filters based on the real-time position changes as it goes through that Cartesian mode of motion. Now, I do recommend that the changes to the PID occur frequently and in small increments. If you were to do this only occasionally with large changes, you're going to end up shocking the overall mechanics as the KP changes by many, many percentage points. It's much better to change them very gently and much more frequently. So again, this is just a real quick block diagram of what's going on. On an axis-by-axis basis, we read the encoder value. We determine where we are within the lookup table. We then set the PID filters as appropriate, and then we move on to the next axis and cycle through. So every 10, 20, 50 milliseconds, we're going ahead and adjusting those PID gains based on the overall positions of the various joints, and that helps minimize the effect of that changing inertia as the position in Cartesian 3 space has changed. Okay, the final axis to discuss is how Galileo controllers can manage a hydraulic axis. So what I'm showing here is a typical application where it's a hydraulic tube bender. So there are standard electromechanical servo motors that position the workpiece into the bender, but then the heavy lifting, as it were, is done by hydraulic ram. So you can see on the left-hand side a relatively straight piece of piping, but then after the hydraulic ram has been extended, that piece of pipe has been bent precisely. So what I'm showing here, again, the darker gray is the tube, the workpiece. Down at the bottom, I have this hydraulic ram, and that is able to extend and cause the tube to bend. Right here on the left-hand side, of course, is the tube bender. And then within the ram itself is the position feedback. Now, the position feedback in this application is different than some of the other applications we've talked about. Instead of using a digital encoder, what we're using instead is an analog potentiometer. An analog potentiometer in this application is a good choice because not only is it very reliable and very robust, but it is actually able to withstand all the outside electrical disturbances that may be present in a machine shop, such as what's coming in from a plasma cutter or an arc welder, you name it. So by going with an absolute analog position feedback, we're able to minimize the overall problems that you might have with digital encoder feedback. So a couple of tools that we had to implement in order to minimize the error and maximize the accuracy. The first is, although the potentiometer does give good, reliable data, there is a certain amount of analog noise. Now, the controller can actually respond to that noise and consider that an actual change of position, and that would cause the hydraulic axis to be relatively nervous and overly aggressive. So the first thing we wanted to do is actually smooth out and help filter out some of those noise spikes caused by external disturbances. The easiest way we found to do that was to add a very simple external circuit that helps filter out those noise spikes because of those external sources. And then the second thing we implemented was an application or a DMC code-based routine to help account for these sort of odd characteristics that come about by using hydraulics to control positioning devices. So here's what the solution entailed. The first thing we did, again, to clean up the analog signal was to use a resistive capacitive circuit, also known as an RC filter. And that was simply added to the analog inputs. Now, those R values, the ohms and the capacitance of the circuit, those could be selected using your basic tools, but if for some reason you needed assistance in choosing those values, feel free to contact Galil. But by doing this and characterizing the noise being sensed by that analog, we're able to really clean up that signal and give us a more precise, repeatable position based on the analog data. Then to implement that, there is a special mode of motion called AF, or analog feedback. And what that does is you simply enable that. The controller then ignores the digital encoder and instead closes the position loop around this analog data. Also included in the solution was the fact that we needed to address the quirks, we'll call it, of hydraulic motor control. The first thing that happens when you're commanding a proportional valve is, of course, as you open the valve, you're really controlling fluid flow. You're not controlling in a linear fashion the force being applied by the motor or the pressure within the ram or anything like that. All you're doing is you're controlling the rate of fluid in or out of the cylinder itself. And because this is the case, there is actually a fairly large amount of deadband, as you can see in this graph below, where I have to move the valve several degrees before any fluid begins to flow. Now, that being the case, we also have to account for the fact that this hydraulic fluid and the ram itself, that system has a great deal of viscous dampening built into it. Naturally, we're controlling fluid flow. So there's really no need to engage the controller's derivative or viscous damping term. So in this case, we simply left KD out of the application altogether. Instead, we rely on the feed-forward velocity, the proportional gain, and the KI term in order to generate the necessary torque in order to move that motion with a minimum of overshoot. And then lastly, the integrator limit term limits the windup of the KI filter and helps avoid any overshoot, which in a pipe bending application is, of course, the worst thing that could possibly happen, because if you overbend the pipe, it's effectively worthless. And then just real briefly to sum up, I just wanted to mention again that no mechanical system is perfect. There's always going to be some quirks. The goal really is to take what you have in your hands and be able to meet the performance spec of the overall application. Whether we do that by the implementation of slight additional hardware or by using either the built-in filters or something else within the controller, the goal is to overcome those mechanical limitations. Second, sometimes very large improvements, like I showed with the dual loop function, those can be implemented with a real minimum of effort. So don't be scared if for some reason you're not meeting your performance spec. Definitely you should discuss that with any of the application engineers to see if there's an easy and low-cost solution available for you. Built into the motion controller, there is a great deal of standard programming and tuning tools, but you really ought to consider that the floor of the capabilities of the controller, not the ceiling. By all means, if you need some special filter or you need an ability to respond to a very unique style of mechanical issues, definitely feel free to discuss your application with the Galil motion controller, because chances are we've seen something similar. We always have a bunch of additional tools in our tool belt. And then finally, I do recommend either hitting up our website at galil.com, or if you're interested, feel free to email or call into Galil. We are more than happy to assist you in determining how best to meet your performance specification with the minimum of additional mechanics and or changes to the overall design. Again, I thank you for your time and thank you for attending, and we're going to move now into a section of questions and answer.
Yes, that's right. So thanks again, Robin, for that informative presentation. So this, as Robin mentioned, this will be the Q&A portion of the webinar, so you can submit any questions you have now, and we'll do our best to get to as many of them as we can in the time that we have left here. So it looks like we've got maybe about 6-7 minutes or so, so we'll see how many questions we can get to. So let me, let's start here. So this was a question, it looks like it was asked maybe towards the beginning of the presentation when we were talking about the first application example there, but there was a question about what about dual loop on continuous closed loop on steppers, on stepper motors.
Mm-hmm. Okay, so dual loop, but using a stepper motor. So with steppers, typically steppers are run in what's considered open loop. So the controller is generating a pulse train and the direction bit, and the stepper motor is expected to just go where it's told to go. If for some reason it is being disturbed by outside forces, that scheme may not be appropriate. And instead you might want to look at using a stepper motor as something which is called a two-phase brushless motor. So we actually commutate the brushless motor, its two phases, based on position feedback from an encoder mounted to the back of the motor. Now, if you engage that scheme, then to the controller and to the dual loop algorithm, that looks exactly the same as a standard brushless servo motor with three phases. So if you had a stepper motor with an encoder on the back of the motor and a linear scale out on the payload, once you use our two-phase brushless control scheme, then by enabling the dual loop, that is invisible to the controller. It doesn't change the overall effect. The only potential drawback is because the stepper motor has a great number of pole pairs, the speed of response of a stepper tends to be lower than it would be for a servo motor. But there are benefits to running a stepper, not only in cost, size, and overall power capability. But as long as the stepper motor meets the performance expectations, dual loop doesn't play a role in the controller knowing that it's a servo versus a stepper.
Okay. All right. Let's go to the next question here. So this is also about the dual feedback loop. Would dual feedback loop with backlash possibly cause limit cycling? Question.
Mm-hmm. Well, yeah. The short answer is it ought not to, because we are positioning the payload based on that linear scale. So unless for some reason the backlash was of such a tremendous magnitude and there were natural resonances within the backlash or compliance because of a timing belt vibration or a chain's resonant frequency or something like that, but those effects, those resonances, can be addressed with a couple of the other higher filters that I hadn't really talked about, including not only our notch filter, which helps null out any natural resonances that are within the closed-loop bandwidth of the axis, but also our low-pass filter, our pole filter, and that helps minimize any sort of high-frequency noise spikes that might cause overall limit cycling of the end effector. But absolutely, if the magnitude of the backlash was tremendous and there was compliance and resonances, additional steps would have to be taken in order to minimize those and still have you result in a very accurate endpoint effect.
Okay. So let's see if we can do. Here's another one. So this one says, coming back to the spring mechanical systems. What if the spring has no effect? I'm guessing it says no. Has no effect in one direction, like for instance in cable guidance.
Okay, so if the spring is being used to pull the payload forward and really plays no role in the reverse direction. And the short answer is, to the controller, at that point, the spring would kind of look like gravity, except gravity is changing all the time. So were that the case, much like my example where the spring effect was bidirectional, in this case, there's simply no effect in the opposite direction. So as you're monitoring the position and you know the stretch of the spring and you know the torque, it's simply that the calculations don't have any possibility of negative OF or one direction or the other. And so it's sort of self-solving in that if you're only pulling in one direction and the spring is only affecting the motion in one direction, then because we're not changing direction, we simply don't have to account for the spring when moving in this direction that never occurs.
Okay. All right. Sounds like that answers it. So we're coming up to 3 o'clock here, so I think we're going to probably have to wrap it up here at this point. So once again, I'd just like to thank you, Robin, for this presentation today. Also, if you'd like to contact either myself or Robin, our contact info is there on the slide there. And just a few more points before we wrap up here. Keep in mind that this webinar will be available online at www.designworldonline.com, and all the registrants will get a copy of the webinar via email. Also, if we didn't get to your question, rest assured that it will be answered. And it will be you'll get an answer to your question. So it's just that we couldn't do it here in real time here. And also, Robin has mentioned how to get in touch with him or any of the other control engineers at Galil Motion Control. And for our sakes here, you can also connect with Design World through many of the usual social media outlets, including Facebook and Twitter and Google Plus and LinkedIn. So if you wish to do that, you can go ahead and do so. And So once again, thank you, Robin. Thanks, everybody, for joining us here today, and hope everyone has a good rest of the day.
All right. Thank you very much, Miles. Thanks, everyone, for attending, and I hope to hear from you soon.
Okay. Thanks, everybody.